welcome everyone. It's great to see you here with us. We had a few, some technical issues at the beginning of our communication today, but this is overcome. And so, Janne, thank you very much for agreeing to promote with us this new Europlanet webinar. So today we have a very expensive topic. We are going to talk about diamonds. We're really looking forward to hear more about these precious time capsules. But before you start sharing your screen and talking about the topic that you chose for today, can you please talk a little bit about yourself, your journey till you decided to work with diamonds?
Yes, I can, thanks. So my name is Janne Koornneef. I'm a researcher and a lecturer at the University of Amsterdam. I should say the Vrije Universiteit, so the VU University of Amsterdam. And I've worked on the continental lithosphere, which is the part where diamonds form already since my master's studies at Amsterdam, which is now 12 years ago. And I've been specializing in analyzing small samples, so small geological samples for their composition. So I'm a geochemist and I'm investigating processes that occur within the deep earth. And one of those processes is diamond formation.
Okay, this is really exciting. I have to say that through this series of webinars, I've learned so much. And I think that if I would start my career now, I would choose a different topic. There's so many things here on Earth that are so amazing and that we really don't know about. Okay, so I will give you the floor 100%. I will be paying attention to the chat. If there is any burning question and I feel that I need to stop you, is it okay? Can I interrupt your talk?
Of course you can, yes.
Okay. Otherwise, you just go through your talk, and at the end we will take all the questions. So if you want to please start sharing your screen.
Yes.
See if the difficulties in communication will not follow us now.
I hope this works. And slowly.
Yeah, this would take some time. We need to have patience. We already have 7 participants here with us.
Okay, so I'm gonna put this to
okay, we can already see your screen, but you have something.
I'm going to go to full screen mode.
Perfect. We can see it perfectly well.
Okay, fantastic.
So I will interrupt you if there is anything that we need. Else, the floor is all yours.
Thank you so much. Okay, so welcome everybody. In the next sort of 30 minutes, I will be talking about diamonds and how we at the University of the Vrije Universiteit in Amsterdam study diamonds to discover how they are formed, where they form, and especially when they are formed. So I think most people will know diamonds because of their use as gemstones in jewelry, because they have such a nice crystal structure and a shiny appearance. Now, apart from the use as gemstones, diamonds are also used by industry because they have a very hard resistance. So they're extremely hard and they have specific thermal properties which make them really ideal for use in grinding and sawing and drilling processes. Now, we as researchers like to use diamonds to investigate how our planet has evolved over history. So to us, diamonds are really precious time capsules from the deep earth because they are formed within the deep earth. Now, before going into how they're formed and where they're formed, I want to briefly mention that except for on our planet Earth, diamonds also occur outside of our planet in our solar system and very likely also outside of our solar system. So this summer, a paper came out in Nature Astronomy that claims that there's diamonds that form within the giant gas planets, such as Neptune, where they are envisioned to rain down onto the core of this giant gas planet, which is really exciting. Apart from that, we find microdiamonds here, these shiny crystals here in meteorites. So meteorites can be found on Earth after they fall onto the Earth. And these are the oldest diamonds that we know, because they think they're formed through collisions between asteroids in the initial stages of the formation of our solar system. So similarly, on Earth, they can also form through impact processes, where they are, for instance, found in impact craters. So I show you here a picture of an impact crater in Siberia. So this crater has a diameter of sort of 100 kilometers. And in the subsurface of this crater, we find diamonds that were formed from the collision of the asteroid with the Earth. So this happened because of the great pressure and temperature conditions that were present at that time. So the subsurface contained graphite, and graphite was transformed to diamond in the impact. Now the diamonds that we find here are relatively small, so only maybe up to 1 millimeter in size. So they're not very suitable to use as gemstones. So where do we find diamonds that we can use as gemstones? So on the Earth's surface, we only find diamonds there when we have an asteroid impact or we find a meteorite. And otherwise, we can only find them there where they're transported from the deep Earth by magmatism. So diamonds form within the deep Earth because they need conditions that have very high pressure and high temperature. So this is the diamond stability zone down here. So they typically form in areas underneath continental plates. So the continental plates are the plates where we live on as humans. And underneath these very old continents, we typically have diamonds forming. The other process where we can find diamonds is in so-called subduction zone settings, where a plate, for instance, here on the left, you see the oceanic plate subducting underneath this continental plate. And also there we have the conditions that are suitable for diamond formation. Now let's zoom in a little bit more in these two types of localities where we can find diamonds. So crustal diamonds form there where we have a continental plate with a crust on top. So the continental crust subducting underneath another continent. So there's a collision zone here, which results in so-called ultra-high pressure metamorphism. And this process transforms an original rock into a different type of rock. And in this process, because we have fluids around that carry carbon into this area with high pressure, we can form diamonds. But what we typically see here is that these diamonds are really small, only tiny. So you see a scale bar here, only 30 microns, so 1/30th of a millimeter. And these diamonds themselves are only tenths, so 100th of a millimeter. So very small, and you won't be able to see them by the naked eye. Now, the other locality where we form diamonds is the locality where we actually form the big diamonds that we like so much. So there is areas on Earth where we have old continents. So there's a continent, this is a cross section, it's a cartoon cross section. So this part here is the continent, and beneath these continents we have so-called cratonic and lithospheric roots. So this continent is quite thick. And this green area here is what we call the lithospheric root. And in the bottom of this root, we have an area where we have the conditions that are favorable for diamond growth. So we need high pressure, high temperature, and we need the presence also of fluids. And these fluids are then rich in carbon, which is the main constituent of diamond. So these fluids are thought to be derived from the process of subduction. So they're introduced into the mantle by subduction. Oops, I'm sorry. And then transferred into the lower or into the mantle above the subducting slab. So we can also form some super deep diamonds here. And then this area is where we have the lithospheric diamonds grow. Now, to get these diamonds to the surface, we need large explosions, so magmatism, to transport these diamonds from these depths all the way to the surface. And this is something that doesn't happen often, which makes the diamonds at the surface really rare. So where do we actually find these diamonds? Well, as I said, we need these large scale eruptions, and these eruptions have their origin at depth of 150 to 450 kilometers depth. And from those depths, they take rock to the surface, and these rocks contain those diamonds. And these kimberlites, as we call them, these explosions and these deposits, so these are volcanic deposits, they contain the diamonds. So these deposits are mined by the mining companies that search for diamonds, such as De Beers, Debswana. And I show you here an example of one of these mines. Usually these are open pit mines, meaning that they're a big hole in the ground, and they take the rock away and then separate the diamonds. These deposits contain diamonds, but it doesn't mean there's a lot of diamond in there. So there's typically only 1 gram of diamond in 1,000 kilograms of rocks. So there's not a lot there, and it's quite a lot of work to get those diamonds out, which is why they're so precious. So where do we find these diamonds? So I show you a map of the Earth here. It's not a very easy map, so I'll try to lead you through. So the occurrences of diamonds are indicated on this map. So in the legend here to the left, we see the types of diamonds that we have. So we have lithospheric and super deep diamonds. We have alluvial diamonds. Those are diamonds that are taken or redeposited by rivers. Then we have the high pressure crustal diamonds that I talked about. And also we have some localities where we find these impact diamonds. Now, especially these lithospheric, super deep and alluvial diamonds are located there where we have the very thick continental crust. So here you can see that in brown and in gray, those are the areas where we have so-called cratons, so the old interiors of continents, and the real old areas and cratons are outlined by these red dashed lines. So we have a huge craton on the north of America, here on Europe, so the Baltic craton. We have a big craton in Siberia in Russia. We have cratons on Australia. We have multiple cratons in Africa, so in South Africa here, Tanzania, Congo, and West Africa. And also we have 2 cratons on South America. Now it's specifically on these cratons that you see that we have the localities where we find diamonds. So all these green and purple diamond symbols here represent mines of where we mine diamonds. So especially in South Africa, there's a lot of mines and kimberlites where we find diamonds. Okay, so now we know where we find diamonds, but what is diamond really? So diamond is actually, it's a mineral and it's made out of pure carbon. So the diamond has a crystal structure in which a carbon atom is surrounded by 4 different carbon atoms. And these bonds between the carbon atoms are really strong, which makes it such a hard crystal. Now, another material that we know that is made out of pure carbon is graphite, so the tip of our pencils that we use. But the difference between graphite and diamond is that graphite has a totally different structure. So it's not structured in a crystal structure like this, but it has a layered structure, meaning that the material is much softer than the diamond. So pure carbon. Now, minerals typically grow from liquids. So we need a liquid or a fluid or melt to grow our diamonds. And the type of fluid that we have determines how our diamond will look like. So what color, what shape, what the crystal, whether it's a very pure crystal or whether it might be. So we have all sorts of types of diamonds, different colors. And we even have these beautiful pink diamonds that of course are the most rare and wanted diamonds for jewelry. So diamonds crystallize from fluids. So in this case, you see that the interior of this diamond is really nice gemstone, very translucent, whereas the outer part of this diamond has a so-called fibrous diamond growth. And this looks much less nice compared to the interior. So this already indicates that we might have different types of growth of this diamond. So we may have had two different events that formed this diamond. So diamonds typically are showing zonation. Similar to a tree ring, we can use the zonation in diamonds to date the diamond growth events. So here we have a nice core, which already shows some interior structures, and a rim around it, which is clearly different from the core. So this image that I show you here has been made by a technique that we call cathode luminescence. So we make a plate, a cross section of a diamond, and we can put it under a cathode luminescence microscope to reveal the growth zonations of the diamond. Now, what we're interested in is how these diamonds grow and over what time scales. Okay, one more example I'll show you here. So this is the research that has been done in our group. So the students in our group made these diamond plates. So on the left, you see the diamond plate as by normal photography. So it's sort of 5 millimeters in size. So it's been cut and polished, and here you see nothing in the diamond. But if you then take the cathode luminescence image of the same cross section, you see that there's quite a complicated structure with a core here and several rims around it, which suggests that this diamond may have grown in several stages. The question is, how do they grow? When do they grow? Over what time scales? Is it days? Is it weeks? Is it years or even millions of years? And in order to know that, we have to date the diamond growth zones. And this is what we focus on in our group. So we would like to date each of the individual diamond growth zones, but that's impossible because we cannot date pure carbon. That's really, really difficult. Now, the good thing is that some of these diamonds have some impurities. And so in here, you see something there. And this is actually an inclusion of another mineral. So this diamond grew around another mineral. And this mineral is a garnet. And that we can actually date. So we're lucky that some of these diamonds are actually not that nice for the jewelry industry, but they are for us. So we want to know whether these diamonds that sit down here in the lithosphere grew instantaneous. Are they all old? Are they grown over billions of years? And that's basically what we want to discover. So what we do is we use the inclusions in these diamonds. So I show you here a nice octahedral diamond with a garnet inclusion here. And this is quite a large garnet inclusion, sort of 200 microns, so 0.2 millimeters in size. And we can use these inclusions because they're not made of pure carbon. They have all sorts of elements inside which we can use to date them. Now, if they have multiple inclusions in several growth zones, we can determine how long it would take for a diamond to grow. Now, what I should mention is that these inclusions, so this one is 200 microns, so not too small, but some of these inclusions are only 10 microns or so, and they're really, really tiny and really difficult to work with. But we have managed to set up the techniques such that we are now able to date these diamonds. And what we use to date these diamonds are isotopes, so radiogenic isotope techniques. Now I have to, of course, explain what an isotope is before I can explain you how this technique works. So an isotope is a species of an element. So if we look at the chemical notation of elements in the periodic table, so we see that each element, such as strontium is one of the elements, has certain numbers listed there. And one of these numbers is the atomic number, which represents the number of protons this element has in its core. So 38 in this case for strontium. So strontium always has 38 protons in its cores, but there's various isotopes of strontium, and those isotopes are species of strontium that have different amounts of neutrons in the core. So the mass number here, so this determines the mass, is the number of protons in the core plus the number of neutrons in the core. And this number can actually vary. So strontium has 4 isotopes, 84 strontium, 86 strontium, 87 strontium, and 88. So the proton number is always 38, but the neutron number varies, and thus varies the mass of the different isotopes. And they have different abundances, and the total abundance is, excuse me, of course, 100%. Now, the interesting thing of isotopes is that some isotopes are stable, but we also have unstable isotopes. And these unstable isotopes, they decay. So we have parent isotopes and daughter isotopes. So we use these isotopes to look at radiogenic decay. So in our case, we've used the Samarium-Neodymium system, where samarium is the parent. So 147 samarium decays to 143 neodymium. And this decay takes place over a certain time scale. And because we know this time scale, and we can determine the concentration of the parent and the daughter in our sample, and we can determine the isotopic composition of the sample, we can determine the age of the sample. Now, this is what we are quite good at the university, the Vrije Universiteit in Amsterdam. And the reason why we're good at that is that we have a special instrument that we use to do this dating, which is called a mass spectrometer. So this is a thermal ionization mass spectrometer. And ours is special because we have a detection system. So here we ionize our samples and we separate the mass of the ions of the different isotopes by this magnet. We collect the isotopes in the back and then measure the composition. And the reason why we can do this on very small samples is that we have specific amplifiers that are really sensitive, which allows us now to date these tiny garnet inclusions. So this is what we did. And I'm gonna show you a case study which we published this summer, or this autumn actually, in Nature Communications, where we found that beneath South Africa, there is a mine where we found that the diamonds have very different ages. So we have very old diamonds, but also much younger diamonds. And that was very interesting. So I will show you what we did. So from this mine in South Africa, the Phoenicia kimberlite, we took 26 diamonds with 26 of these garnet inclusions. I'll show you an example here. And we dated them using the technique that I just briefly explained to you. So Samarium-Neodymium isotope dating. Now, the new thing about this was that we used single inclusions, so only one inclusions to determine the age of the individual inclusion, whereas previous work always took pools of these inclusions because they simply weren't capable of analyzing a single inclusion. So what they found previously was that the age of the diamonds from this mine was 2.3 billion years. So this was the known age. So our data is shown here. So what I show you is the model ages that we calculated from our isotope data on the x-axis in billions of years versus the number of occasions that had this age. So the number of inclusions was 26. And we see that our garnet inclusions had an age range between 4.2 billion years, that's very old. So the age of the Earth is 4.6 billion years old. So it ranged from 4.2 billion years all the way down to 0.6 billion years. And what we also see is that there's actually two dates that are prevailing. So 9 inclusions have an age of 3.0 billion year, and 11 inclusions had an age of 1.1 billion year. Whereas the pooled age that I just told you about is here, 2.3. So this age was obtained by taking 30 inclusions, or at least 30, and determining the age. Well, you can see nicely that this age is an average age of the two populations that we have now discovered. So here I show you actually the same data, but in a so-called isochron diagram, where we can derive the precise ages out of. So I plot the neodymium isotope composition on the y-axis and the samarium, so the parent over daughter elemental ratio on the x-axis. And all samples that lie on a line in this diagram are from the same age. So the samples here that lie on the green line define an age of 2.9 billion years, or 2,945 million years, whereas the samples that lie on the blue line here define an age of 1.1 billion years, meaning that these diamonds grew in events that are 2 billion year difference in age. So that's a very, very long time. Now, what we then also discovered that these two different events were characterized by really, really different conditions. So the old diamonds, so the 3.0 billion year diamonds, showed evidence for formation from relatively cool fluids based on the compositions of these inclusions. And these are now trace element compositions, so the chemical compositions. Whereas the younger diamonds typically showed conditions for formation from hot melts. So not alone they were formed in very different times, but also by very different conditions. And especially this younger age was actually quite surprising to us, because typically people think that this type of diamond that we investigated is always old. So always Archean or around 3 billion. So the 3 billion is not unexpected, but the 1.1 billion year was unexpected. Now, when we looked at the area around the mine where we found we had our diamonds from. So this is the Phoenicia diamond mine here in this diamond shown there. And what we see is that around this area, we have these deposits indicated by blue that have exactly the same age as our diamonds. And these deposits represent volcanic deposits, so lavas. And these lavas were thought to have been erupted over a huge area. So this full area here was once covered by these lavas. So a big magmatic event was suggested to have happened at 1.1 billion years. So we interpret this event to be responsible for the diamond growth that we discovered. So there must have been an event like an upwelling from the deep earth that caused melting in the mantle below this area to result in melts to pass through the lithospheric mantle. And this melt would have precipitated or formed the diamonds that we see. And it would also have caused the deposition of these lavas on the surface of the earth. So that was quite amazing. So what we found is that we actually have 2 billion years age difference between these younger diamonds that was quite unexpected and the older diamonds. And this means that that diamonds do not grow instantaneously over days or weeks, but they can actually have cores that are, well, yeah, they form maybe in the Archean, whereas the rims around it could be very, very recent. And this is implication of how we think that this process of diamond formation happens. So these diamonds that sit here will likely record multiple events that happened within the region. And these can be subduction events. It must mean that subduction already happened 3 billion years ago, because we need those fluids to form the diamonds. So that's important. And it also means in this case that we had an event at 1 billion years ago that created enough heat to have diamonds grow. So that's basically what I wanted to tell you. And I'm happy to receive any questions if you have some.
Janne, thank you very much. That was indeed really very interesting. I don't know if you have been accompanying the chat, but the participants are saying amazing webinar, great webinar. So they're really very happy to have had the opportunity to listen from an expert like you about diamonds. I mean, I had no idea that was like that. I had no idea. So that's absolutely amazing. And we do have some questions here. So first we have questions that have been sent to us throughout the weeks. And so this one is, how can we identify a true diamond? So of course, several of them you already answered during your presentation, but never too much to refer to that. So how can we identify a true diamond? And this was sent by Janne de Fatima Moreira Branco from Brazil.
Okay, yeah, well, thanks for the question. That's a very good question, because of course, if you find something which is nice and shiny on the street, you would like to be sure that it's not, or it is a diamond. So diamonds, as I said, are one of the hardest materials that we find. So glass is much less hard than diamond. So if you would have a diamond, you could easily scratch a piece of glass with it. So that would be a very easy test, of course. So the hardness, you can test the hardness and see if that complies with the hardness of diamond. The other thing is, of course, the composition. So diamond is made of pure carbon. So if you have a way to determine the composition, then that is the way to find out whether it's diamond, of course. Crystal shape could be used, although there is more minerals that have similar crystal shapes as diamonds. And also the shiny luster is very specific to diamond. But again, not everything that has a shiny luster is a diamond. So, but you would have to test several things to be sure.
So you enter a party and you see everyone using shiny things. Can you detect a diamond? Do you know?
Oh, that is very difficult, because you can also make diamonds and fake diamonds. So you can make something really shiny, which is not a diamond. So that's quite difficult, to be honest.
Okay. Oh, that's nice to hear, because I mean, I could never see the difference. But then again, who am I to talk about diamonds? I mean, I really don't see these particularities that you have been mentioning. They have so many. Okay, so Wilson Canelo from Colombia is asking, are there also gems outside the Earth? I think you already answered that, but maybe you want to elaborate a little bit more.
Yes, so yes, I started my talk with the diamonds that we find outside of our planet. So there's definitely diamonds in the solar system and very likely also outside of our solar system. But these diamonds are typically very small, so not as nice and precious as the ones that we have on Earth. Basically, diamond can form anywhere where the pressure and temperature conditions are correct. So we can envision many other places in our in the solar system and also outside, where I guess that we will have diamonds. But to be honest, I'm not an expert in that field.
Okay. Another question is, what would you consider most important step of the scientific method? And this was sent by Panagiota Alexandra Frati, Greece.
What would you consider?
The most important step of the scientific method.
Okay, for our method. In this case, that is definitely the ability, our ability to be able to measure very, very small samples for the isotopic composition. So we have now been able to date individual inclusions, and we are able to do this, and we will continue working on this, which reveals the growth history of individual diamonds. And that is, I think that's the key thing of this research, which makes this so amazing compared to what was previously possible.
Okay. Another question is, what is the biggest size of a diamond that could form inside the Earth?
Ooh, good question. To be honest, I'm not sure, because of course we only base our knowledge on the diamonds that we find. The diamond that I showed in the first slide, so on the cover slide, is actually, I forgot to mention in the introduction, but this diamond is exceptionally large. So this is called an Oppenheimer yellow diamond, and its size is 253 carats.
Are you showing this? No, you're not showing.
No, I can go back to it, I guess. It's all the way at the beginning. Maybe I should just exit.
It was a very nice slide for introducing the topic.
Yeah. So this slide, let's put it back. So this diamond here has a size of 253 carats, and a carat is the same thing as 0.2 grams. So this means this diamond is 50 grams. And I think that means it would be something like this size. So that's a very, very large diamond, but these are extremely, extremely rare.
Okay. So how many times you get diamonds in your hands?
Okay, well, we have, actually, I took some. We have quite a lot of diamonds here at the university that we use for our research purposes. So I can show you some examples, I guess. So there's a jar here, which contains...
so can you stop sharing your screen? Stop sharing your screen so that it's easier for us to...
Okay, yeah, sure. Okay.
In a bigger form.
Yeah.
Perfect. Now maybe you can show again.
So there is a jar here, and this jar contains 2 cubic diamonds. These are not very translucent, as you can see, because they have a specific crystal growth structure. The size is almost 1 centimeter. Well, a bit less, I guess. So we have quite some diamonds around. I have a few of these jars also with bigger ones here. So what we do with these diamonds, of course, because we're using the diamonds for research, is destroying them.
Oh my God, I have a diamond in my hand and I'm about to destroy it. What do you do for a living? I destroy diamonds.
Yeah, well,
very cool.
Yeah, the reason why we can do this, of course, is that these diamonds that we obtain through De Beers, De Beers is a diamond exploration company. These are the diamonds that contain inclusions and impurities. So for jewelry purposes, they're less interesting, but for us, they're actually really interesting. So that's a good, it's a good deal, actually.
Of course, of course. Then we have another question that is from Jaffas. How do you get fluids carried to such depth within the subducted lithospheric slab?
Oh, very good question. So the subducting slabs that I was talking about were oceanic plates. So these were crusts that once were on the ocean. So, and during the formation of these plates within the ocean, there's lots of hydrothermal circulation, which brings seawater into the crust. So a lot of the water that we bring into the mantle comes from the sea. So hydrothermal alteration, also of course there's a big sediment package onto these slabs that subduct. So that's where we get the water from, actually from the ocean, so from the surface, and we transport it down through subduction of these content of these lithospheric plates.
Okay. Another question from the same person is, have you dated diamonds from different areas, cratons?
We are working on that. So we are currently mainly focusing on diamonds from the African continent. But I actually did some work also on super deep diamonds from the South American continent. And colleagues of ours are dating diamonds from Australia. So we are actually working on diamonds from all sorts of places. And also previous work here at the VU was on Siberian diamonds. So yes, we are actually studying diamonds from all over the place.
Okay. And the last one from the same person is, are kimberlite eruptions still possible today?
Good question.
I have to say, I know he's a geologist.
Yeah, I think so. The fact that they have not occurred recently make people think that they are not. But to be honest, I don't know. I don't think so. I don't think that the conditions are still such that we can have kimberlites, but I'm not an expert, and I think there's still lots of debate about this question.
Mm-hmm. Okay. Then there is another one. I think this will be the last one that I will post to you today, which is, did you research any diamond coming from space? Did you
no, I did not myself. No, I did not. No, I'm really an Earth scientist. I'm not a planetary scientist. No, I would like to, but no, we have not.
Do you know people who have studied diamonds coming from space?
Not in our group. No, I know. Sorry, I don't know anyone that has done that. No.
Okay. Well, I think we already thank you. A lot of questions. Thank you very much, Janne, for this very good webinar. We're very glad that you had the opportunity and the time, and you were willing to share your expertise with us. We hope you come again. And I'm sure that this webinar will be seen by a lot of people, and lots of people might be wishing to send questions to you. And if that is the case, sure, we will be sending them around. So thank you very much. Thank you. Thank everyone for participating. And we see you all in the next year. We have the holiday season coming. Hope you all have a great holiday season, that you rest, you get energized. And we will be back in January with more webinars from Europlanet. We have already a very interesting list. It's going to be a Christmas surprise to you. We will announce them soon. I also take the opportunity to say that we are already announcing our summer schools and winter schools. So come back, and thanks everyone. Janne, thank you very much. It was an amazing webinar.
Thank you for giving me this opportunity. It was really nice to do. Thank you so much.
Great, great. Thank you.
All right.
Bye.
Bye-bye.